Hello everyone, welcome back to another PySpark interview prep session. Today we are discussing an essential technique for optimizing data processing in Spark repartitioning a data frame. Repartitioning plays a big role in balancing workloads, improving parallelism, and managing memory effectively in distributed environments. In this video, we'll cover how to repartition a data frame in PySpark and why it's so important for performance. Introduction. In PySpark, repartitioning a data frame is the process of adjusting the number of partitions it has, which is a key step in optimizing data distribution and performance in distributed data processing environments. Partitioning determines how data is divided and processed across the cluster, directly impacting both parallelism and efficiency. By repartitioning, we can balance data more evenly across partitions, helping to prevent issues like data skew, where some partitions are much larger than others, which can slow down processing. Additionally, repartitioning can reduce the amount of data shuffling between nodes, which is particularly beneficial in operations like joins and aggregations. PySpark provides two main methods for repartitioning: repartition and coalesce. The repartition method allows for increasing or decreasing partitions involving a full shuffle to redistribute data evenly across all partitions, which is ideal for achieving balanced parallelism. The coalesce method, on the other hand, is a more efficient option for reducing partitions when a full shuffle is not required, as it minimizes data movement. Together, these methods provide flexible ways to optimize data distribution, making repartitioning an essential tool for enhancing performance in PySpark applications. Methods for repartitioning a data frame. The repartition method in PySpark is a powerful tool for reshuffling data across a specified number of partitions, which helps to achieve balanced parallel processing in distributed data environments. With repartition, you have the flexibility to either increase or decrease the number of partitions according to the needs of your workload. When repartition is applied, Spark performs a full shuffle of the data, meaning that it redistributes records across the cluster to ensure that each partition has an even share of the data. This full shuffle operation is ideal for situations where we want to increase partitions for more parallelism, or when we need to redistribute the data based on specific columns, such as in join or aggregation operations. By redistributing data across partitions, repartition enables Spark to process large data sets efficiently, especially in cases where even data distribution can prevent bottlenecks and optimize performance. The syntax for using repartition is straightforward. You can specify the desired number of partitions as df.repartition numpartitions to adjust the partition count. Alternatively, if you want to repartition based on certain columns, you can specify both the number of partitions and the column names, such as df.repartition numpartitions column underscore name. This column-based repartitioning ensures that records with the same key are placed in the same partition, which can significantly reduce shuffling in downstream operations. Overall, repartition is a flexible and essential method for fine-tuning data distribution across Spark tasks, allowing for efficient parallel processing and optimized performance in distributed applications. Example: DEG. In this example, we begin by setting up a Spark session with the application name repartition example, which serves as our entry point for working with Spark's distributed data processing capabilities. We create a sample data frame that includes employee data with three columns: name, department, and salary. This dataset is small but provides a useful illustration of how the repartition method can be used to adjust the number of partitions in a data frame. Next, we apply the repartition method to increase the number of partitions to 10 by calling df.repartition10. This operation creates a new data frame, df underscore repartition, with 10 partitions. By using repartition, Spark performs a full shuffle of the data, redistributing records evenly across the specified number of partitions. This reshuffling is essential when we want to achieve balanced parallelism, especially for larger datasets where evenly distributed data across partitions can help improve performance. After repartitioning, we confirm the updated partition count by calling df underscore repartition dot rdd dot getNumPartitions, which outputs the number of partitions. In distributed data processing, increasing the number of partitions is particularly beneficial for tasks that require high parallelism, as it allows Spark to distribute work evenly across executors, avoiding bottlenecks and making better use of cluster resources. This example demonstrates how the repartition method is a valuable tool in PySpark for optimizing data distribution and enhancing performance in large-scale data applications. Methods for repartitioning coalesce. The coalesce method in PySpark is specifically designed to reduce the number of partitions in a data frame without performing a full shuffle, making it an efficient choice for cases where you need to decrease partitions but want to add the overhead of a complete data redistribution. By consolidating adjacent partitions, coalesce reduces the number of partitions in a way that is faster and more resource friendly than repartition. This method is particularly beneficial for situations where the data distribution across partitions does not need to be perfectly even, such as when preparing data for saving to a file where fewer larger output files are preferable. When using coalesce, Spark combines adjacent partitions without moving records across all nodes, which helps minimize data movement within the cluster. However, unlike repartition, which performs a full shuffle to evenly distribute data, coalesce does not ensure balanced partitions, so some partitions may end up with more data than others. This lack of even distribution can be a trade-off for faster execution, but in cases where precise partition balance is less important, coalesce is a highly efficient choice. The syntax for coalesce is straightforward df.coalesce numpartitions, where numpartitions is the desired reduced partition count. This makes coalesce a valuable tool for optimizing write operations as it reduces the number of files created when saving data to storage, resulting in improved performance for downstream tasks. Overall, coalesce is a practical and efficient solution for reducing partitions in PySpark, particularly when a full shuffle is unnecessary. Example. In this example, we use the coalesce method to reduce the number of partitions in a data frame without incurring the cost of a full shuffle. Starting with a data frame that may have multiple partitions, we call df.coalesce2 to reduce the number of partitions to 2. This operation creates a new data frame df underscore coalesce with only 2 partitions. The benefit of using coalesce is that it merges adjacent partitions rather than fully redistributing the data across the cluster, making it a more efficient option when reducing partitions, particularly if a balanced data distribution across partitions is not critical. After applying coalesce, we verify the new partition count by calling df underscore coalesce.rdd.getNumPartitions, which outputs the updated partition count as 2. The coalesce method is especially useful in situations where fewer partitions are preferable, such as when preparing to save data to a file, as it reduces the number of output files generated. This approach helps streamline storage and read performance, particularly for downstream tasks that may need to process or load the saved data. By reducing partitions efficiently without a full shuffle, Coalesce offers a faster way to consolidate data, minimizing network and compute resources. This example illustrates how Coalesce is an ideal choice in PySpark for reducing partition counts while maintaining good performance, particularly when an even distribution across partitions is less essential. Choosing between repartition and coalesce. When working with partitions in PySpark, Selecting between repartition and coalesce depends on your specific needs for data distribution and performance. Use repartition when you need to increase the number of partitions to enhance parallelism, especially for large data sets that would benefit from additional partitions. Repartition performs a full shuffle, redistributing data across all nodes to create balanced partitions. This full shuffle is ideal for cases where an even distribution is crucial, such as when preparing for join or aggregation operations, as it ensures that data is uniformly spread across partitions and reduces potential bottlenecks in processing. On the other hand, use coalesce when you only need to reduce the number of partitions and want to avoid the computational cost of a full shuffle. Coalesce consolidates adjacent partitions without redistributing data across all nodes, making it a more efficient choice when decreasing partitions, particularly if exact data balance is not required. This approach is beneficial for saving data to storage as it reduces the number of output files, streamlining data management, and improving RAID performance for downstream tasks. Since coalesce doesn't shuffle data, it's faster than repartition and is often preferred for write operations or for scenarios where the dataset has already been partially filtered or reduced. In summary, choose repartition for even data distribution and increase partitions, and opt for coalesce when reducing partitions efficiently without a full shuffle is the priority. Understanding these distinctions helps optimize resource utilization and performance in PySpark applications. And that's a quick overview of how to repartition a data frame in PySpark. We've seen how repartitioning can improve parallelism and optimize data distribution for complex transformations and actions. If you found this video helpful, please give it a thumbs up, subscribe for more PySpark tips, and hit the notification bell to stay updated on our latest content. Thanks for watching and see you in the next video.